So hello students, welcome back. The today's topic is why do LEDs emit light while other diodes don't? Let's try to understand. So first of all, what is an LED? LED stands for light emitting diode. So basically it's a diode that has got the capability to emit light. So the definition of an LED says that it's a semiconductor diode that can emit light when electric current flows through it in the forward direction. So that is an important point. Whenever a diode is forward biased, it can emit light. However, when the same light emitting diode is reverse biased, it cannot emit light. So the symbol of an LED looks something like this, wherein it actually resembles that of a normal diode. However, these two outward pointing arrow marks suggest that the light is being emitted. Okay, next, how does an LED work internally? Well, it's very simple. LED works basically on the phenomena called electroluminescence. So what do we mean by electroluminescence? Well, in simple words, it is nothing but when the input is electrical energy, it gets converted to light energy. Okay, so basically it's the process of the conversion of electrical energy to light energy. Well, how does a LED look like internally? So as already mentioned, it is basically a PN junction diode. But when we look at the materials with respect to an LED, they are slightly different. We know that a normal PN junction diode which cannot emit light is usually made up of either silicon or germanium. However, the light emitting diodes are usually made up of compound semiconductors like gallium arsenide, gallium phosphide, gallium nitride and indium gallium nitride. So basically these are all compound semiconductors. Okay, so we'll have to understand about these things. Okay, compound semiconductors are very popularly used in LEDs. So what does LED structure consist of? Well, it has got P region, N-type region and basically a active region. Okay, so what do we mean by P-type region? Well, P-type region is the space where holes are the majority carriers. N-type region, free electrons are the majority carriers, and it is mainly in the active region where the light is being generated. So this is how LED structure internally looks like. Okay, so basically it's a very simple structure. So at the bottom there is substrate and on top of it N region and then followed by the active or the depletion region and finally the P-type region. Okay, and you can very clearly observe that how light is being released. When we say light, it is nothing but photon. Now with respect to commercialization, this is how a LED looks like. So if you carefully observe, it is seen that on the top there is epoxy lens followed by the wire bond and there is a small reflective cavity and you can find the anode as well as the cathode. So coming to the working of LED. Okay, so now let us try to understand the working of LED. Well, when the light emitting diode is forward biased, which means P region is connected to the positive terminal of the battery and N region is connected to the negative terminal of the battery. So when the light emitting diode is forward biased, due to the applied polarity, so holes are being forced to move from P region to N region, and similarly the electrons are also forced to move from N region to the P region. But during this course of time, when an electron comes in contact with a hole, there will be recombination. Okay, so it is very clearly observed that most of the free electrons and holes do get recombined in the active region. Okay, so the active region is also called as depletion region. Now it does not mean that there will be no recombination in the P region or in the N region. There will be recombination. However, when it comes to percentage wise, most of the electrons and holes do get combined in this active region. So we can very clearly say that the maximum intensity of the photons or the light being emitted from a light emitting diode will be from the active region itself. Now, the electron hole recombination results in a photonic emission. So this is a very simple animation which shows when electron and a hole do get recombined, a photon will be released. Now the question is, why do different LEDs produce different colors? Well, the answer is very simple. Different semiconductor materials have different band gap energy. Now we'll have to understand that band gap is a material characteristic which differs from every material to material, which means, say for example, if we consider silicon, germanium, gallium arsenide or any other compound semiconductor, say for example indium gallium arsenide, then the band gap of all these four semiconductors will not be the same. They will be different. So now the question is, the light emission is always related to semiconductors' band gap energy. Now, when the band gap energy of every material is different, then do they emit light of the same wavelength? That is the question. The answer is no. So this particular table very nicely shows us that if the material being used in the light emitting diode is of gallium arsenic phosphide, then the light emitted will be of red color. Suppose if the material is gallium phosphide, then the light emitted will be green in color. If the material is gallium nitride, then the light emitted will be blue. If it is a combination, then we can also get a white light out of an LED. One important note is that the light emission, which means either the wavelength or the frequency, is always related to the semiconductor's band gap energy. So this particular simple equation relates the energy band gap with respect to the wavelength or the frequency of the light being emitted. So let us try to understand it in a little more detail. So here EG stands for energy band gap of a particular material. Okay, now suppose, let us consider that there is a material called indium gallium arsenide. Let us just assume indium gallium arsenide. So basically this is a compound semiconductor material. Now if we just talk about the energy band gaps, then EV and EC. So EV stands for the valence energy level and EC stands for the conduction energy level. Now Whenever the light emitting diode is forward biased, the electron from the valence energy level jumps into the conduction energy band. Now after some time during the recombination process, it again has to come back. Okay, so during the forward bias it gains some energy E and it jumps into the conduction energy level, but during the recombination process it has to emit that energy that it had acquired. So this additional energy will be released in the form of light. Now the color of this particular photon will depend on the energy band gap, which is mentioned like this, Eg. Okay, so the distance or the Eg determines the frequency or the wavelength of the light that is being released. Okay, and with respect to the relation, it is very clearly observed that the energy band gap is inversely proportional to the wavelength of the light being emitted, which means higher the energy band gap, lower will be the wavelength of the light emitted. Okay, so in this case H stands for Planck's constant and c is the velocity of the light. So just to put it in terms of the proportionality, we can also say that the energy band gap is directly proportional to the frequency, or the energy band gap is inversely proportional to the wavelength. Okay, so that means if we increase the energy band gap, the frequency of the light that is being emitted also increases, whereas the wavelength it decreases. Okay. Now a very important question is, why doesn't an ordinary silicon diode glow? Okay, so the answer is, an ordinary silicon diode primarily emits the energy in the form of heat energy rather than photons. So it is very clearly seen that ordinary silicon diode, which is usually made up of silicon or germanium, it emits the energy in the form of heat energy, or is phonons. Okay, whereas the compound semiconductor like indium gallium arsenide emits the energy in the form of light, which is photon. Okay, so it's very clearly seen that such normal diodes, which are normally used in the rectifiers, cannot emit light. Okay, so they get usually heated up rather than emitting light. Now what are the important characteristics of LEDs? There are some few important characteristics, like the forward voltage of a LED is typically between 1.8 to 3.6 volts, and it also depends on the color. Forward current is usually in the range of 10 to 30 milliamperes. The polarity sensitivity is also there. Low power consumption, well, LEDs consume low power. They are very energy efficient when compared to normal CFL bulbs, and of course they have a long life which can last up to 25,000 to even 1 lakh hours. So that means LEDs are extremely important. They are highly energy efficient, long lasting with respect to usage. They are small and fast, which makes them the ideal contenders for electronics and digital displays. So we normally see that nowadays most of the traditional bulbs are being replaced by light emitting diodes, and of course they are reliable and durable. and they are also available in many colors without filters. Okay, so this particular diagram shows the difference between a normal CFL bulb and a LED bulb. Okay, so finally the common applications of LEDs are mentioned in the slide. They find many applications. Okay, so normally they are being used in the indicator lights, TVs, monitors, mobile displays, traffic signals, the headlights, brake lights of almost all the automobiles. They are used for the decoration purpose, household lighting. They are also used in digital clocks, and we also see them in remote controls. Okay, so thank you for watching.